Good evening, everyone, and thank you so much for joining me for the power of bioengineering. Tonight, I'm inviting you to imagine a world that is led by bioengineers, one where we are recreating life itself, building artificial tissues, and mimicking the divine blueprint of life itself. In this world, science and nature really come together hand in hand, where bioengineers like me are trying to mimic the intricate structures that we see in nature to heal both people and the planet. For me personally, this has been and is still a lifelong endeavor, and one that reminds me constantly of the profound connection of understanding the world in which we live to transform it for the better. So, as you've already heard from the introduction, I'm an entrepreneur, and I get very excited about building real-world solutions that tackle surgical problems, because I'm very passionate about doing what I can to improve healthcare. And the way I've got here is because I've been a bioengineer for probably 20 years now, most of my adult life. And so tonight I'm going to be trying to channel all my passion and some of the learnings that I've taken throughout my time in my career there, and really highlight some of the snippets of the key innovations that I've been fortunate enough to be part of and design with some of the fantastic teams that I've had the pleasure of working with. Some of those great minds are here in the audience today. I think I can just about see a couple of them. I've positioned them really well to take all the difficult questions at the end, so do give me a nod if I can't see you. But you're probably wondering what a bowl full of bubbles and all of these different props are doing here as well, right? Well, in addition to being a bioengineer, I'm also a science presenter. And in some circles, I'm known as Professor Lightning, particularly when I'm trying to entertain young kids and sparking their curiosity to get them excited about science. I've also been fortunate enough to be one of the Royal Institution science presenters, trained right here from the fantastic team. So when I knew I'm giving tonight's lecture, I couldn't resist. I thought I had to include some of their legendary demos to really dazzle and delight you tonight. So in true RI style, we will be having some fun. We'll be learning some science along the way. And I should say I will be keeping an eye out for some volunteers a little bit later on to help me with some of these demonstrations too. Okay, so in the next hour, I'm going to walk you through some groundbreaking innovations that are addressing these unmet clinical needs, lots of different tissues around the body. And hopefully by the end of the talk, you'll get a better idea of how bioengineering is really working at the intersection of different disciplines that all come together to really create some really remarkable things. We'll be exploring how everyday materials, like eggs, are being used by bioengineers like me to transform and heal the body as well. And we're also going to be looking at how we draw some inspiration from everyday processes, because bioengineering is all around us, you just don't know it. So, what is bioengineering, and why is it so important? Well, you're here, so you must have a little bit of an idea of what bioengineering is. It's similar to what I just said earlier, how in the way that we're combining science, engineering, technology to really innovate new medical devices, but also materials and processes. In bioengineering, we can use this for a diverse range of things, but I'll be focusing on how we're harnessing it for improving human health. So, as we continue to innovate for health, we must be mindful of the planet, right? There's 8.2 billion of us on this planet, so there's no surprise that the impact that people have is going to be detrimental on our planet. We all have a responsibility to protect it. We all rely on the Earth's resources for our food, our water, our energy. So regardless of what sector you work in, we all have a responsibility to protect it. We can't just leave it to the environmentalists. So that's where bioengineering comes in, and it's quite critical because it's a fantastic discipline that has the power to do both, protecting our health, but also trying to protect our planet while we do that. So as bioengineers, how are we doing this? Well, we're trying to develop biodegradable materials. This will try and replace the plastic materials. So in healthcare, these are typically used for surgical bandages, which you will hear about a little bit later. But they have huge impact on the planet because obviously they're plastic, they're like most everyday materials. They can be damaging to our environment. So as bioengineers, we're trying to find materials but also processes that use fewer resources of the earth. So just to really bring home the damaging effects of these traditional plastics that we could use, we all know that it can be quite damaging to the environment, right? The production of these plastics often rely on the use of fossil fuels, which are non-renewable resources, and as you can see, they generate a lot of toxic waste. So it's no surprise that these processes and these plastics are contributing to lots of pollution and lots of climate change, unfortunately. So bioengineering is great because we're trying to create eco-friendly materials that don't have these damaging processes, but are also going to heal and restore our body. And this is where our collagen comes in. Now, some of you have probably heard of collagen already. You might be familiar with it. You might be taking it as supplements for your hair, your nails, your bones. Some of you might be putting it in your protein shakes to bulk up your muscles. Everyone's heard about collagen or creams as well. But scientists love collagen because it's really our building block. It's the most abundant protein in the body. It's in most of your tissues. And scientists call it as biocompatible, and that means that because it's already in your body, it's readily accepted. That minimizes the risk of rejections and complications that might happen. So it's a really good material to start to use. In healthcare, it's already being used as sutures and skin grafts, and we'll hear a little bit later about how it's being used for wound dressings as well. Then there's also bioplastics, and we'll talk a little bit about that later. But bioplastics are great because they're also used from renewable biological sources like plants. Things like plants or algae, as you can see in the pictures, they reduce the environmental impact because they can degrade over time. So unlike the traditional plastics that stay there, these can degrade naturally into the environment. So they're great for medicine and also for the planet. So how exactly do we use these materials like collagen and like bioplastic to really engineer tissues that will repair, replace, and regenerate all of these different tissues in the body? So now we're going to get into the science. So to do that, what we need is 3 key factors. And we'll talk about each of these in turn. So we do need cells. Cells are like the basic unit of every living thing. We need to be able to grow those cells on a material, right? So if we're trying to deliver something into the body, we need a way to be able to grow them and take them from the bench into a patient. And we need to grow this in the right environment. So cells, let me move this butane out of the way. Cells are, as you can see from the picture, cells are in all of living things. They're so small that you need a microscope to see it. And so we've got this picture here to really kind of bring to life and show you what these cells are. These are probably fibroblasts, but we won't go into that just yet. So because scientists, we do fantastic things, but we can't create something living from nothing. We still rely on taking cells from either a donated tissue or an organ and extracting that and growing that up, letting the cells multiply. So we're still dependent on a cell source. And there's lots of different places that we can get cells. Depending on what tissue you're interested in engineering, you would get a cell from that corresponding tissue, donated from tissues that people have donated for research. Then we need a material on which to grow it. This is a great picture showing how a cell actually attaches to the material. In our case, we're trying to use those natural materials. And like your jumpers have fibers, these materials also have fibers at that kind of level of that structure. And cells really respond differently to different materials. So we have to try and understand that if we're trying to recreate tissues too. And then, of course, we need to grow it in the right environment. So cells here are cells, once we've grown them on the material, they take cues from mechanics. So if there's different forces that are being applied to that material, the physical cues, they are also indicating what these cells are going to turn into. So by physical cues, we mean the surface of the material, what the topography looks like. And they're also taking biochemical cues, right? So we have to give the right nutrients, the right food, the right growth factors in order to get these cells to survive and perform the function that we're hoping they will. So let's get into our first clinical need. And one of the ones that I've been fortunate enough to work on was that of trying to repair the cornea. This work was undertaken in the lab of Professor Judy Daniels over at Moorfields Eye Hospital at UCL. And we were trying to repair the cornea after patients who suffered from blindness affected either by acid or alkali injury, or perhaps a genetic disease. Now, what is the cornea? So, as the picture shows, it's the outermost transparent surface of your eye, and it's what acts as our window to the world. It allows light to pass through and hit the back of your eye where the retina is, and this is what enables our normal vision. Now, for the cornea, transparency is absolutely key. The structure of the cornea, which we'll hear a little bit about, is what gives the cornea the transparency property. So, unfortunately, there are 10 million people that suffer from corneal blindness worldwide, so it's a huge unmet need. Typically, these patients have had the acid or alkali burn or the genetic disease, like I said, and their damaged cornea looks like that one in the top picture. Quite opaque. It has blood vessels that maybe grow from the surrounding tissues, and that, of course, reduces and obscures their vision. Typically, these patients would receive a transplant. So that would be a donor cornea transplanted from someone on their death. So we're hugely dependent on that, but there is really limited supply of donor tissue. Just to give you an idea, to put it into context, we need 70 corneas a week just here in the UK to meet the demand for these transplants. But 88% of organ donors, even though they're happy to donate their heart, their lungs, their liver, are still not willing to donate their eyes. And so the type of research that we do gets really, really difficult. Just to have a little bit of audience interaction, if you're happy to raise your hand, if you would consider donating your eyes. I won't be collecting them at the end, don't worry. But just to get an idea of what these percentages, are they, raise your hand if you are registered as a donor or you would consider raising. Oh, we got much more hands when I said, would you consider? Okay, great. And then could you keep your hand up if you are willing to donate your eyes? Oh, wow, I should have come sooner. This would have been great for our research. Fantastic, thank you so much. So, yeah, hopefully things are shifting, and of course the law is shifting as well, like in terms of compulsory, or opting out in terms of organ donation. And this helps bioengineers like me, particularly when we were doing this work. It's really difficult to get hold of good quality corneas. So actually what we were trying to do were create alternative treatment strategies. So instead of using one cornea to treat one patient, what we would do is we would use stem cell technologies to extract those cells and grow them up so much that we could create a cell bank. And we would do that so that we could treat multiple patients. So a little bit now about the structure, because I was telling you it's so important for the transparency. So this is what the cornea looks like. I won't go into the huge details of all the different layers, but what I want you to really remember is that the bulk component of the cornea is called the stroma, and this is the collagen-rich layer. So the collagen material I was explaining to you, that's where we find it in the kind of bulk component. And the beauty of the stroma is that it has a really highly organized architecture. So beautiful, in fact, that it creates that basket weave pattern that we are trying to replicate. And that basket weave is what allows light to be passed through and hit the back of our eye onto the retina. That structure is synthesized by the cells that live in it. And so in this case, it's called stromal cells. But the key thing really is that where we get loss of this structure, this results in loss of vision. So you can imagine if there's a tear to your cornea, or there's an injury, or there's an acid burn, that's going to really, it's going to really remove all of the nicely organized structure that was there. And that is what causes part kind of bad vision or blindness in some severe cases. So what were we trying to do? Well, like I said, we were trying to extract the cells from that stromal layer, and depending on how we grow those cells, we're able to grow lots of different types of cells. So we have fibroblasts, we have some stem cells in the middle, and we have keratocytes. So at this point, it's not really important what the cells are called, but you might have already heard about stem cells, and they're quite an exciting cell because they have the ability to self-renew, and they can divide depending on the conditions in which we grow them. That we can push them down different fates, and we can make them be what we want them to be. So the stem cells were quite exciting. So we would get the donor cornea, just to give you an idea of what we do in the lab, because no one really sees us in the lab. We kind of hide behind our lab coats. But what we do is we take the donor cornea, we would dice it up into small pieces. No biology is possible without a Petri dish, so we would grow them in our Petri dish, give it the right nutrients, right? So I was telling you about the environment being so key, the correct nutrients and growth factors. And then we would plate them in these tissue culture flasks, as you can see in the picture. And the good thing about these stem cells is that they would grow overnight. I would have to be in the lab all the time, just trying to keep these cells alive. Because, of course, when they take over their flask, they need to be divided even more. They need more space to divide. So then you've got to go in, culture them, move them into fresh flasks. And this process goes on and on and on until we can get huge cell banks that we can then keep and freeze down for later use for creating our corneal tissues that we ultimately want to give back to patients. So stem cells, I could probably give a whole lecture on stem cells, but here it's just enough to say that these were adult stem cells. So most of our tissues have adult stem cells that we can extract. We don't always have to rely on embryonic stem cells. And so this is the case in the cornea. That's exactly what we were doing. Right, so we've heard a lot about the cells. The next thing is the material. And you've probably guessed that the material I'm going to talk about is, in fact, the natural material like collagen, right? Because this is all going to be about collagen, a lot on collagen. But what does collagen look like when it's not in your protein shakes or your supplements? What does it look like when scientists like me are trying to create artificial tissues? Well, it does, in fact, look a lot like jelly. Now, jelly usually makes everyone really happy when they see a bowl full of jelly. But jelly is great. It is gelatin, so it's quite similar to collagen, not quite the same. But I shared this picture because I wanted you to understand the consistency of jelly. So collagen is a great material. We've already talked about its advantageous properties. The great thing is we can fabricate it really rapidly. And in science, that's really important. You want to keep costs down, but you also want to do things quite quickly so that you don't infect the tissues, you're not keeping them in the lab for a long time. And also this collagen, we're able to tune the properties of it. And it's compatible with a variety of cell types. So, of course, these are the gels that we decided to use. But the thing that these gels lacked, and in fact jelly as well, if you think about jelly when you're trying to eat it with a spoon, you're often running around on the plate just trying to get it on the spoon. And of course surgeons wouldn't be able to pick that up and put that onto someone's eye either. So we really needed a way to make it much stronger. How could we do that? Well, I'm pleased to say that this technique, called plastic compression, was developed by the late Professor Robert Brown, who I was fortunate enough to do my doctorate with. For the science buffs in the crowd, you might see it in the literature with the acronym RAFT, if you want to read the papers. But it was a really simple process. And I think that's the beauty of science. I love things when they're really simple. So the way this process works is that here we have our collagen gel. So if you imagine that jelly, we've seeded it with cells. So in our case, we were building the cornea. So we put corneal cells inside. And we just placed it between two plates, and underneath we had some absorbing filter paper. Because what we were trying to do was to remove the water. Because if we removed the water, we are able to increase the strength of this tissue, right? So removing 99% of the water with this process increased the collagen density, which turned it from a jelly-like substance into a much more thin tissue membrane, quite similar to what your skin would look like. And so that was great, because now it meant we could pick it up and we could suture it, we could transfer it from the dish into a patient. So a really simple technique made it much, much stronger. We then worked for many years, now also working with Professor Judy Daniels, to try and really develop this process further. Because in science, we need to make things much more rigorous and much more standardized. And that earlier diagram that you saw, we were just doing it on the bench, so it wasn't very reproducible. Here we worked with a company, so this is where bioengineering really thrives, actually, working with biologists, engineers, and industry as well, to really develop a process and make it much more standardized. So it turned into this current format that you can see here. And so now, instead of doing it on the bench, what we were doing is we were making it in these small dishes. The filter paper, similar to the type of filter paper you'd use if you were drinking filter coffee. We could do away with all of that, and now we could replace it with just a single porous absorber. And that's really important, because when we're manufacturing things clinically that are going to go in patients, the whole process is highly regulated. And I think this is the part of science that people don't often see and can't appreciate. But these things take years to develop. They take multiple huge teams on the regulatory side, on the clinical side, just to get something ready for a patient. So, like I said, this was many years of work, and I've condensed it in just a couple of slides. But you can see the best thing about it was that it's really rapid. So we are able to make these tissues in less than an hour, really. And now that they're in a dish, it means we don't have to probe them, we don't risk infecting them. And we can now seed some cells directly on top. So here's the finished result. We would then seed our corneal cells on top. And because we're putting collagen gels in these little dishes, we could play with the volume, we could play with the collagen density, and that was really important for trying to tune the transparency and the strength of our tissues. And so this diagram shows you how if we made it much thicker, the thicker gels and the highly concentrated gels were much more opaque. So we tried to find the sweet spot, what would be just right, in order to develop a transparent corneal stroma. So I'm pleased to say that these processes and these kind of technologies are being used and have been used in patients at Moorfields. Because it went through the whole kind of standardized process, it's now available commercially as a kit, and people are using it for lots of different things, not just corneas as well. That takes me on to our next little bit. So we've talked a lot about corneas, but like I said, now we can make these collagen tissues in a dish and we can tune the properties. We can use these tissues to repair other parts of the body. So I guess at this point, I want you to imagine when you get a cut or an injury, or let's say surgeons are trying to repair a tissue inside your abdomen. We need to be able to stitch it back in exactly the same structure, right? Similar to knitting in that it needs to follow a specific pattern. Otherwise, what's left is the fibers that we try and repair aren't lined up in exactly the same way, and of course that means the tissue won't be as strong. And so when the fibers are all kind of disorganized, that can lead to scarring. So scientists are trying to repair those kind of scars, internal scars, using surgical bandages, similar to the ones here. But the key thing that they're lacking is that they don't mimic the structure of our native tissues. So inside your body, they're highly aligned, particularly your abdomen. The connective tissues that lie underneath your muscles are really highly aligned. And so these bandages just don't make the cut, in my opinion. They're also plastic, right, which we don't like. We're trying to preserve the environment. But the key thing from a health perspective is that they're over-engineered. They're far stronger and they're far stiffer than they need to be. And of course, patients that are receiving some of these bandages have reported a lot of pain. And so as bioengineers, we're all about trying to create something that integrates with the body better. And why not try and create something that mimics the architecture of our natural tissues? So I spent a lot of my career trying to recreate the architecture of natural tissues in different parts of the body. And really, it was just to highlight here to you how we have the disorganized scar tissue, which we're trying to move away from and create. If we're trying to put tissues in the body, we want them to be nicely aligned in that way. So how do we do it? Well, we can look to everyday techniques to inspire us. And for this part of the project that I'm going to share, I had an Italian student that was working on it called Alessandra. And so we'd spend a lot of Friday afternoons in the lab after lunch. So obviously talking, because she's Italian, we talk a lot about food and pasta. And so we were really racking our brains thinking, how can we create a process or a method that can help us align our collagen gels so that they mimic that of the tissues in our body? And we looked at a pasta maker. We thought this could be great. Stay with me on this one. I'll try and explain what I mean. So similar in a similar way to the way this pasta maker works, you can see we're rolling the pasta through. And this is flattening and changing the structure of the pasta somewhat. So we thought if we're able to take these forces that are in the pasta maker, if we're able to create a roller that we could then roll on the surface of our collagen gels, could we use this process to try and push the collagen fibrils along that same direction? So we experimented, and we found that we could create this technique called horizontal shear flow, which we're about to publish. And it's really simple. Just like the pasta maker, we used a makeshift roller that we put together in the lab with the materials that we could find. And we rolled this across our collagen gels. So the collagen gels, when we make them, they have this random alignment, right? But what we were trying to do was to recreate that highly aligned structure, just like this one here. So by applying shear forces on the surface of the gel, the hypothesis was that we would cause enough force to rearrange the architecture of our collagen fibrils. And so we confirmed this with lots of cutting-edge microscopy called second harmonic generation microscopy. And the top picture there shows you what the collagen architecture looks like. So here you can see that this would be the direction in which we were rolling the gel, and you can see that the collagen fibrils are also aligning in that direction. So we got really, really excited. We thought, this is great. It's just a matter of minutes. We're able to engineer something and completely change the architecture. But we wanted to check whether, if we put cells on here, would the cells also follow those same cues? So we seeded some cells on top. So this method didn't rely on cells, which was great, but we seeded it on top to see whether they follow the same arrangement, and they did. And that's really important because we want to give the cells the right structural cues to be able to synthesize more organized collagen, right? If they're placed in a collagen where it's disorganized, they will also create disorganized collagen. So getting the structure was really, really key. This was really exciting because one, it was really simple, right? It doesn't cost a lot. That's really important because actually previous studies and other scientists have used huge magnetic fields, which is huge equipment and can be really costly just to try and align collagen. Some studies have looked at using the contraction forces of cells, but of course you then need to be able to put cells inside your collagen, and that's not always great. So here we were able to do it just with collagen alone and in just a matter of minutes. Now, similar to the plastic compression process, we wanted to be able to try and standardize this, right? Science is all about rigor and accuracy. So we wanted to move away from this kind of handheld device and try and create a much more standardized way. Luckily, I had a lot of engineering students to hand. And so over the years, they worked on lots of different iterations of this device, and it's still not finished. But this is science in progress, so I thought I'd share it with you. And basically, this prototype is showing you a device where instead of making one gel, we could now create 2 gels, and possibly maybe multiple more gels, considering however many rollers you use. And it's just much more controlled. So that was the kind of concept of how we could turn something really simple, use engineering and biology, and bring it together. Okay, so for the next bit, I'm going to talk a little bit about another material now, and that is bioplastics. Oh, this is thirsty work, so forgive me for keep drinking. Okay, so bioplastics. I was fortunate enough to work with a dear colleague of mine, Federico Trotta, who's somewhere in the audience. Somewhere, I can't see. Okay. But he has his own company called Metalchemy, and he develops materials and processes that support the deployment of sustainable chemistries to create things like these bioplastics, which I'll show you in a second. And these are great because they prevent the hazardous toxic chemicals and they enable a greener future. We could use these bioplastics for health, but he's also using them for things like packaging. I will share this around, so feel free to have a feel. This is an actual bioplastic that we've engineered. I will start it off here and see where it ends up. But when you get hold of it, you'll see that it's a really cool material. Again, we can really tune it quite well. And he has some great chemistry processes to do that. So we wanted to explore using this bioplastic alongside our collagen gels as well. But he was also synthesizing nanoparticles using much greener synthesis methods that are less toxic than existing commercial nanoparticles. So again, on the environmental theme, we were really excited to try and use some of these materials. Nanoparticles have been used quite extensively, and it's known that they're really good for wound healing. We wanted to see whether we could embed the nanoparticles from Metalchemy into our collagen membranes, but also into the bioplastics. And could we actually use these for wound dressings? So what are nanoparticles, for those of you that don't know? Well, they're actually really tiny, as the name suggests. So they are nano-sized. And that means they're about 1,000th the width of a human hair. So really, really tiny. And this picture at the top shows you it in context to other things as well. But the huge advantage about nanoparticles is that they have these antimicrobial properties, in that because they're so small, they're able to penetrate microbes and eliminate them. So they stop them from growing. And this guarding against bacteria is really, really important for wound healing, right? We don't, of course, we don't want our wounds to get infected and take longer to heal. We got very excited that these nanoparticles, if we incorporate them into our wound dressings, we could heal wounds much faster, and we could do it in a much more safer way, infection-free. So before we can't kind of catapult ourselves and just put these into patients. So you have to step back and do lots and lots of studies. So the first step for us was to create these materials, embed our nanoparticles inside the bioplastic, which is just made from agar or algae. And we also compared it against our collagen materials too. And we thought that, like we said, it could have different potential applications in wound healing. It could be used for things like diabetic foot ulcers, which is a huge burden on the NHS, or indeed later down the line in bone regeneration too. And I won't show you all the data, but this was just to really show you how we were able to successfully embed them. This picture shows you the collagen fibers. And in the red circles, you can see the tiny, tiny nanoparticles that are embedding themselves in the structure. What was important for us was to see that once we've embedded them, the cells that we then seed on top or inside the gel would remain alive and they wouldn't die. And so we were successfully able to do that. And so that was a huge step forward for us. So we carried on in our quest for looking for other sustainable natural materials that could serve as wound dressings. And I got chatting with my colleague David Chow over at UCL, who had a cracking idea of using eggs. He was actually repurposing eggs to create lots of different medical materials. So I thought, rather than, I guess we wanted to try and show, everyone knows what an egg looks like, we should probably try and crack open one. So I could probably maybe just throw it to someone in the audience who would like to catch the egg. Oh, are there some on the balcony? I don't know. You guys at the bottom should be quite brave about it. No one on the front row. I was hoping I couldn't aim that far. Oh, I could try the kids over that side, maybe. Let's try and give it a go. So can we see if we can catch the egg? The people at the front seem a little bit worried. I'll do my best. I'm not the best thrower, but we'll give it a go. Are we ready? Who am I throwing it to? The little boy here? Yes? You ready to catch? I'll try not to hit the gentleman there. Are we ready? 3, 2, 1. Oh, you got caught. A round of applause. Very good. Excellent. Good catch. We didn't crack it open, but I think these ended up to be quite hard-boiled eggs, so that's okay. No mess. RI will be very happy with me. Okay, so he had a cracking idea, but what part of the egg could we actually use? So it's not the yolk, and it's not the white. In fact, it was the membrane, the eggshell membrane, just inside. So if you've ever had your breakfast and you're trying to peel the egg, that little bit of membrane that always sticks to the shell, that's a really annoying bit. It happened to me this morning at breakfast. That's the bit that they're using for creating lots and lots of different things. And why? Well, it's predominantly made of collagen, so you already know about collagen and its huge, great properties. It has a unique structure and composition, but it can have lots and lots of different applications in the body. There are some challenges still. We need to try and enhance the mechanical properties. We're trying to also incorporate different things in the eggshell membrane to really enhance the properties too. But it's a great. The reason we got really excited about it is because it is typically a waste product, right? But it's a sustainable material that we could use to create implants for our eyes, our teeth, or indeed, in our case, for wound dressings. So I hope you'll all agree that it is an excellent material. I'll stop with the egg puns now. But it has all of those unique structures, it's biocompatible, it's anti-inflammatory. And so David Chow is still leading on this work. He has his own spin-out company called Reovum, if you're interested in having a look. But what we wanted to do was actually collaborate with Metalchemy as well, and their fantastic nanoparticles. We thought, can we try and put these nanoparticles in our eggshell membrane? And will they prevent microbes from growing? So we did just that, and this picture, as yucky as it is, what it shows is the top column here shows you the microbial growth over time, up to 21 days, I believe. So these are the Metalchemy nanoparticles, and the one below are the commercially available ones that aren't so eco-friendly. But what you can see is that actually we got a lot less growth of microbes, and so this was great. These were our nanoparticles grown on the eggshell membrane. And so this was great. It meant that we could, prevent the takeover of microbes even at day 21. So this got really, really exciting. And so this hopefully gives you a little bit of a glimpse of how we are enhancing the biomaterials. We've talked a bit about the structure. We've talked about things that we can incorporate inside of it. So hopefully that gives you a good idea. So towards the last part of the lecture, I wanted to talk about the future of surgery. Before I do, I'll just have a sip of water. So the future of surgery, I've been working on trying to prevent scarring for my entire career. And so for me, the future of surgery, an ideal future, would be one where we don't cause any scars at all, even if we're operating. It would be one where we can automate it, so we could use robots, maybe not quite like this one, but some type of robot. And also we could do procedures remotely. So people in remote parts of the world could have access to some of the cutting edge and trained surgeons in other parts of the world, making surgery much more accessible. Luckily, this is no longer a dream. This is exactly where we are headed. It's looking like a little bit of science fiction, right? Or a future where robots take over the world. But we're really seeing a rise in surgical robots, ones that can perform delicate tasks with real precision and real accuracy. And these systems are guided by skilled surgeons. So we're not looking to replace surgeons, but we're looking to provide them with tools that enhance that. So we've already had a couple of revolutions in surgery, interestingly enough. In the 1980s, surgery started with big open surgery. So we would have surgeons would cut you open to get to the organs that they're trying to repair. And although it could have health benefits, it does leave massive scars, and that gives rise to lots of complications as well. But luckily, as we got into the 2000s, this evolved to kind of keyhole surgery or minimally invasive surgery. And what you're seeing here is the Da Vinci robot. These are robotic arms that are operated by surgeons, but they operate through small incisions that are made. So we no longer need to make those huge incisions, but instead we can make small incisions, and these instruments can get inside the human body with real precision and actually perform surgery with much more accuracy than we could just with our bare hands. But that's not enough, right? Where we see the future is really endoluminal surgery. And what does that mean? Well, it means these are procedures where doctors can use the natural pathways, like your digestive tract, to actually get inside and operate, avoiding large incisions and avoiding small incisions altogether. However, these instruments are lacking, so we're not quite there yet. What we do have are endoscopes, so you might be familiar with these. These are tubes that are placed inside your digestive tract, one way or the other. I won't go into the gruesome details, but these typically have a camera on them, right? So they're mainly restricted for diagnosis. They're not really equipped yet to have surgical tools on the end of them. But the surgical field is expecting a revolution, particularly in the treatment of bowel cancer, as more and more people are being diagnosed with early stage cancer at stage 1 and 2 because of this rise in diagnostic tools, these endoscopes. And in the same way that heart surgery went from open and invasive surgeries to the use of stents that we can place now in our arteries, we expect the advancement of surgical tools to one day render open surgery almost obsolete, as we give surgeons the tools to operate in the entirety of the colon, all along its twists and turns. That's the dream. And I'm thrilled to say that together with my co-founder, Arnau, who has invented the next generation surgical robot, we're building Serpenta. It's a company set to provide surgeons the tools to operate anywhere in the colon, removing cancers and tumors with ease and with precision. We're currently building this startup with the support of Zinc Venture Capital, and we're very, very excited about our next steps. Our vision for Serpenta is to spearhead the revolution in surgical care, one that will redefine what's possible in operating rooms just like this across the world. We're building a future where surgery is smarter, safer, and far less invasive. So, the future of our health, and indeed the health of our planet, really lies in the hands of our innovators of tomorrow, especially in those young minds, especially those here today. I hope that you've seen we are not just dreaming of a better world, but we're actively building one. One breakthrough, one discovery, one step at a time. So in leaving, I will leave you with this quote because I feel it really articulates the honor and privilege that I've had to work with amazing colleagues and collaborators without whom none of this work would be possible. And I wanted to express my gratitude to the RI as well for giving me the opportunity to stand right here in this theatre and follow in the footsteps of some of the greatest scientists before me. And thank you all for listening.